Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions from October-November 2022 paper 2. In the last two videos, we have discussed all the questions from mechanics, and in this lesson, we will focus on waves, electricity and radioactivity. If you need solution of mechanics questions, you can search for October-November 2022 paper 2 part 01 and part 02. And in today's lesson, we will finish all remaining questions, mean we will talk about question 4, question 5 and question 6. And we will discuss these questions in detail so you can have better understanding of these questions, and also you can improve your conceptual understanding of these topics. Let's study together, let's improve together. In today's class, first of all, we will start from part D because this was not included in the last video, and then we will go to question 4. For part D, it is given to us when the sphere moves from the position shown in figure 3.1 to position shown in figure 3.2, the upthrust on the sphere does work. Assume that resistive forces are negligible. We can ignore resistive forces in this case, and we need to explain why the work done by the upthrust is not equal to the gain in elastic potential energy of the spring. So first of all, let's try to understand this scenario, this situation. Let's try to understand. First of all, water level in this tank is low. As water level in the tank is low, then we added more water to the tank. As more water is added to the tank, the water level will rise. So in this case, upthrust will do work on the sphere and sphere will rise. So when sphere will rise, sphere will gain GPE. So this one will gain GPE. So some of the work done by the upthrust is used to increase the gravitational potential energy of the spring, and some of the work done by upthrust is used to increase EPE, elastic potential energy of the spring. So that's the reason the work done by upthrust is not equal to the gain in EPE, because some of the work has been done to increase GPE of the sphere. So simply you can say in this case, as sphere has gained GPE, as sphere has gained GPE, that's the reason work done by upthrust is not equal to gain in EPE. As sphere has gained GPE, that's the reason work done by upthrust is not equal to gain in EPE. So that's all what you need to write down, and this question has only 1 mark. For question number 4, part A, it is given to us a progressive longitudinal wave travels through a medium from left to right. Figure 4.1 shows the position of some of the particles of the medium at time t0 and a graph showing the particle displacements at the same time t0. Particle displacements to the right of their equilibrium positions are positive, and particle displacements to the left are shown as negative on the graph. So we need to understand in this case to the right is positive, so very important one. So simply you can mark this one, and period of the wave is given, that is capital T. For part A1 on figure 4.1, we need to draw circles around two particles which are exactly one wavelength apart. Very straightforward question. So we can take any 2 points on this wave. Let's say we take this point and we can take this point. So simply you need to circle these particles. This is one particle and this is another particle, and these are one wavelength apart. So simply you need to circle this one. You can choose any other points also possible. You can take this point on the wave and you can take this point on the wave. So you can also circle this particle, you can also circle this particle. Two particles you can circle which are one wavelength apart. So you can do this particle, you can do this particle, or you can do this one and this one. So result is the same. So they are one wavelength apart from each other. For the second part on figure 4.1, we need to sketch a line on the graph to represent the displacements of the particles for the longitudinal wave at time t0 plus t by 4, means after 1/4 of cycle. So in order to answer this question, first of all, we will look at motion of these particles. The particle at this point, after 1/4 of cycle, this particle will go down because it will follow the coming wave. So it will go down. So after 1/4 of cycle, this particle will be here. And if we look at this particle, after 1/4 of cycle, because this particle will follow the coming wave, this particle will go up. So after 1/4 of cycle, this particle will be at the top. And this particle will follow the coming wave because the wave in this case case is moving to the right, so it will follow the coming wave, mean this will climb up. So this particle will reach equilibrium. So this is equilibrium. Particle will be here after 1/4 of cycle. So it started from here. You can also draw small arrows. This particle will go down, this particle will climb up, and this particle also will climb up. If you look at this particle at this point, this particle will follow the coming wave, so it will go down. So after 1/4 of cycle, this particle will be here at this point. If you look at this particle, after 1/4 of cycle, actually this particle will go down. So after 1/4 of cycle, this particle will be at this point. It will follow the coming wave, means it will follow this part of the wave. So it is here, so it will go down. So it will come to this point. Now, if you look at this particle will follow the coming wave, and this is positive displacement. So it will go up. This particle will go up. So after 1/4 of cycle, this one will be at the top. And particle at this point, it will follow the coming wave. So this particle will climb up. So this will go to this point. And particle at this point, this particle will follow coming wave, and this is negative displacement. This particle will go down. After 1/4 of cycle, this particle will be here. So this is, first of all, you need to understand after 1/4 of cycle where these particles will be. And if you look at this particle here, we can extend this wave. So the wave is like this. So this particle will go down after 1/4 of cycle. Particle at equilibrium, this will go down because it will follow the coming wave. So this particle will be here after 1/4 of cycle. Now simply we need to connect these points. We need to connect these points. So we can draw this sinusoidal curve, and this sinusoidal curve is representing displacement of particles. So simply we can draw like this. So this sinusoidal curve is representing displacements of particles after 1/4 of cycle. So this is how you need to draw. Now let's go to next part. For next part, we need to state direction of motion of particle C at time t0 plus t by 4, means after 1/4 of cycle. Particle C, so this particle C. Now if we draw dotted lines, you can see here this particle, you see displacement here after 1/4 of cycle, displacement is positive. If the displacement is positive, it means particle is moving to the right. So simply you need to write down particle at C after 1/4 of cycle is just moving to the right, because to the right is positive. So particle is just moving to the right. So this is how you can answer this problem. For part B, it is given to us the frequency of the wave in A is 16 kilohertz. The distance between particles X and Y is 0.19 meters. And we need to calculate the speed of the wave as it travels through the medium. So we need to calculate speed. Frequency is given to us, and the distance between particle X and Y is given. This distance is given to us. So if we can calculate value of lambda, we can calculate speed. Speed is simply equal to F times lambda. And frequency is given to us, that is equal to 16 kilohertz. So we can multiply this one with 1000. And the wavelength has to be 2 times of xy. So lambda is 2 times of xy, and xy is equal to 4.19. Now simply we need to multiply, and we can find the value of V. And value of V in this case will be equal to 6100 meters per second. So this is how you can calculate. Quite straightforward one, and up to 2SF you can write down 6100 meters per second. For part C, it is given to us a longitudinal sound wave is traveling through a solid. The initial intensity of the wave is I0. The frequency of the wave remains constant. Very important one. Frequency remains constant. And amplitude falls to half of its original value. We need to determine in terms of I0 the final intensity of the wave. So first thing we need to understand in this case, intensity is directly proportional to amplitude square. So in this case we can say initial intensity is I0, so amplitude we can also say is A0. We need to find out the final intensity, so we can say final intensity is IF. This is what we need to calculate. but final amplitude is given AF, that is equal to A naught by 2. Now we need to find out I final, but also we need to understand that I naught over A naught square, this one is equal to constant, means the ratio between intensity and amplitude square is constant. So we can simply then write down I final over A final square. This also has to be constant. So we need to find out IF. So we can rearrange this. We can write down IF in this case has to be equal to I naught times A final square. So this is A final square, and this one has to be divided by A naught square. Now we can plug in value of A final. So we have I naught, A final is A naught by 2 square divided by A naught square. From here we can write on I naught, and here we will have A naught square, and this one will be divided by 4A naught square. So this we can cancel with A naught square, we can cancel with A naught square, so we left with IF. So IF in this case is equal to I naught by 4, or we can say this is equal to 0.25 times I naught. So this is our final answer. So simply we can say this is equal to 0.25 of I naught. So this is our final answer. This is how you can approach. This is a very systematic approach. If I look at this question, amplitude become half, so the intensity has to be 1/4. So directly you can find the answer. But this is a systematic approach. You can answer this question. It's better in your exam, write down all the steps. Even if your answer is wrong, still you will get some marks. So in your final exam, always write down all the steps. For part D, it is given to us the sound wave in C now meets another sound wave traveling in the opposite direction. We need to state a condition required for these two waves to form a stationary wave. So for any stationary wave to be formed, there are certain conditions that need to be fulfilled. First condition is that type of wave. Only same type of wave they can form stationary wave. Means sound waves, they can form stationary waves with sound waves. Light can form stationary waves with light. Microwaves, they can form stationary waves with microwaves. So same type. And the second condition is that they need to be traveling in opposite direction. So the second condition we can say opposite direction for stationary waves. Opposite direction. And same frequency is also very important. Same frequency. They should have same frequency. Then we can observe stationary wave. And also amplitude. If they have same amplitude, then we can also observe stationary waves. So same amplitude. Same amplitude. But if you look at given conditions, this is given to us same type because another sound wave, mean type of waves is the same. Opposite direction, they are traveling in opposite direction, so that is also given. So we can say same frequency, we can say same wavelength, or we can say same amplitude. But in this case, we will simply write down same frequency and wavelength. So if you write on this point, you will get 1 mark. This has only 1 mark. For the second part, we need to state two ways in which a stationary wave differs from a progressive wave. There are many differences between stationary waves and progressive waves. So let me explain you some general one. The first main difference between stationary wave and progressive wave is that stationary wave does not transfer energy, but progressive wave transfer energy from one point to another point. So that's the reason stationary waves, we call them also standing waves, because they do not transfer energy. So that's the reason we call them standing waves. And other difference is that all the particles on progressive wave, they have the same maximum amplitude. But in case of stationary waves, amplitude of particles is different. Particle at the node has zero displacement, and particle at antinode has the maximum value of amplitude. And other particles, they have between maximum and zero. And stationary wave, they consist of nodes and antinodes, but progressive waves, they don't have nodes and antinodes. So these are some main difference. So if you write on 2 points, you will get 2 marks, because this question has 2 marks only. So let me show you the answer, how you can write down your answer. So this is how you can write down your answer. You can mention only 2 points you need to answer this question. So first first point you can say a stationary wave has nodes and antinodes, and progressive wave doesn't have nodes and antinodes. So you will get 1 mark. So this will be 1B mark. A stationary wave does not transfer energy, and progressive wave does transfer energy. You will get another B mark. So if you write on these 2 points, you will get 2 marks. But also it is important to understand other points as well. Different points on stationary waves have different amplitudes, but all points on a progressive wave, they have the same amplitude. Stationary wave has adjacent particles that are in phase. Mean one particle and the next particle, they are always in phase. Mean particle between two antinodes, between two nodes, they always vibrate in same phase between two nodes. And adjacent particles on a progressive wave are out of phase. So this is also difference. You can also mention this one. You can mention any 2 points, but it is important to understand all these points. The difference between progressive wave and stationary waves. For question number 5, part A, we need to state Kirchhoff's second law. And Kirchhoff's second law simply tells us sum of EMFs in any closed loop, sum of EMFs in any closed loops is equal to sum of PDs in any closed loop. So this is how we can state Kirchhoff's second law. So let me show you the answer, how you can write down your answer. This is how you can write down your answer. It is very important that you mention a closed circuit, not simply a circuit, a closed circuit. So if you write down this one, you will get 2 marks. 1 mark you will get if you have written this part, then the second mark for writing this one. For part B, it is given to us 3 identical cells, each of electromotive force 1.5 volts and internal resistance 590 milliohms are connected in parallel across a conductor as shown in figure 5.1. The conductor is composed of 2 cylindrical sections A and B, and total resistance of the circuit is 2.2 ohms. We need to show that resistance of the conductor is 2.0 ohms. So in this case, total resistance is given. So simply we can say R total of the circuit is given, that is equal to 2.2 ohms. We need to find out resistance of conductor. We can say R conductor, resistance of conductor, and resistance of the conductor will be equal to R total minus total internal resistance, R total, small r total. So total resistance of the circuit is 2.2, and if we have value of total internal resistance, we can calculate resistance of conductor. So it simply means that this whole circuit we can replace just with one cell with internal resistance here, and you can draw here. This one is resistance of conductor, means R conductor, and this is the R total. This is R total, and here we have cell, so this is 1.5 volts. So this is whole this circuit you can replace with this single circuit, with this simple circuit. So we need to find out R total. As these internal resistance, they are connected in parallel, so simply we can say R total in this case will be equal to 1 resistance divided by number of resistors, just divide by number of resistors, and we will get our final answer, that will be equal to 0.197 ohms. And we can simply write down this value here, and this is about 0.2. So the final answer will be 2.0 ohms, and this is resistance of this resistor. So this is how you need to approach this type of problems when cells they have internal resistance. Why we design circuit like this? So in this case, the lifetime of the battery will be longer, so we can use this kind of circuit for a long time. So this is the main benefit. For the second part, we need to calculate current in the conductor. So we have already discussed we can replace this circuit with this one simple circuit. So simply we can take one cell and we can replace this resistance with R total. R total we have discussed, that was equal to 0.197, and this resistance we have calculated, that was equal to 2.0, and this cell EMF is 1.5. So now simply we need to calculate current. So current will be equal to V divided by total resistance of this circuit, that is equal to 2.2. So the final answer in this case will be 0.68 amps. So the benefit of this circuit is that internal resistance we can decrease in this case by connecting more cells in parallel, and also we can increase the lifetime of the battery. So the lifetime of the battery will be longer and energy lost will be lower. So these are two benefits of this kind of circuits. For part C, it is given to us two cylindrical sections A and B of the conductor in figure 5.1 are made from the same material and they have the same length. The diameter of section A is 4.3 mm and diameter of section B is 7.6 mm. The resistance of section A is RA and resistance of section B is RP, and we need to find the ratio between RA and RP. So the best way to start this question is we can start with R. Resistance is equal to rho L by A. It is given to us these two conductors, they have the same length, they are made from the same material, so their resistivity is also the same. So it simply means that RA, this is equal to rho times L, and this one is constant. So simply we can say this is equal to constant, and this means that RA times AA, this one will be equal to RP times A times P. Now from here we can further simplify. We need to find RA by RP. So we can say in this case RA divided by RP, this one will be equal to AB divided by AA. So in this case we have B, diameter of B is given. So first thing we can do is we can write down this one in form of diameter. So we can say pi by 4 dB square divided by, so this is pi by 4 dA square, but in this case we can cancel pi by 4 with this pi by 4. So we have diameter of B is given 7.6. So we can write down 7.6 times 10 to minus 3 because this is in millimeters. Actually, it is not important because this ratio it will be cancelled, but it's better if you write down square divided by. We have dA, that is 4.3 times 10 to minus 3 square. So in this case, this will be cancelled. 10 to minus 3 will be cancelled with this one. So simply we left behind 7.6 square. This will be divided by 4.3 square. Now if we solve this one, our final answer will be equal to 3.1. So this is the ratio between A and B. So this is how you can approach this problem. For the second part, we need to calculate the ratio between average drift speed of free electrons in section A and average drift speed of free electrons in section B. So it simply means that we need to calculate VA over VB. So we need to find the ratio between VA and VB. So first of all, we need to understand in this case how to use transport equation. I is equal to NQVA. But for this question, it was given to us that they are made of the same material. So it means N is the same. So N is the same. Q is also the same because this is constant. And current also is the same because current is the same, they are connected in series. So I is the same, N is the same, Q is the same for these two. So we can write on here I over NQ, this one is equal to VA. But this is constant for A and also constant for B. So it simply means that this is equal to constant. So simply we can write down constant. Now we can write down VA times AA. This one has to be equal to VB times AB. So we need to find the ratio between VA and VB so we can rearrange. So here we will get this is AB divided by AA. So we can write down in form of diameter because diameter is given. So pi by 4 dB square divided by pi by 4 dA square. So in this case, pi by 4 will be cancelled. So this one will be cancelled. So dB, because dB is given to us, that was in millimeters, and dA is also in millimeter. So we can take square of this one. We don't need to convert into meters because that will be cancelled. So simply you need to divide this one by 4.3 square and you will get the same answer as you got in part 1. So the answer for this one is also 3.1. For part D, it is given to us the circuit of figure 5.1 is altered by removing one of the cells. State and explain the effect, if any, of this change on the potential difference across the conductor. So first thing we need to understand, in this case we have removed this cell. So we have only 2 cells. So we can redraw this circuit. So we have one cell, EMF is 1.5 volts. So this has EMF 1.5 volt. And here we can draw total internal resistance. So we can say R total. And also we can redraw conductor. So we can replace this one with one resistor. Let's say resistance of this conductor is R. Now we need to understand what is effect of removing this one cell on internal resistance. So in this case, R total, this one will be equal to 590 milliohms divided by 2 now, because we have only 2 cells connected in parallel. So in this case, this R total has been increased as compared with the last part. So we will say R total increase. If R total increase of this circuit, it means the energy lost will increase. So we will say the V lost inside the battery, this one will increase because R total means the internal resistance has been increased. If internal resistance has been increased, cell EMF is the same. So the potential difference across this conductor, so we will say that one will decrease because this one has increased, so this one has to decrease. So the potential difference across this one will decrease. So this is how you can answer this problem. So these points you have to mention in your answer. So let me show you the answer. And so this is how you can write on your answer. The first point, you can say the combined internal resistance of the cells will be greater. So this one has increased, so you will get 1 point. And the second mark you will get if you have written more lost volts inside each cell. So more energy lost. So this one you will get another point. And then you will say potential difference across conductor will decrease. So you will get 3 marks. So the potential difference across conductor decreases because EMF of each cell is the same. For question number 6, part A, it is given to us the nuclide carbon-14 is unstable and undergoes beta minus decay, emitting a high energy electron and an anti-neutrino to form a new nuclide X. The equation for this decay is shown and we need to complete this one. For this question, it is given to us this is beta minus decay. So the best way to start is we can write down this is beta minus decay. So this is electron, beta minus decay. So if this is 1, this one has to be 7. And in beta decay, there is no change in mass number. So this one is 14. So this is simply how you can complete. For part B1, we need to state the equation for beta minus decay in terms of fundamental particles involved. So if you look at this equation, in this case, we can see the proton number increases by 1. As proton number increases by 1, it simply means that 1 neutron change into proton. So we can say in this case, 1 neutron means up, down, down quark. It changes into up, up and down quark. And plus we have this is electron, this is already fundamental particle, and we have electron anti-neutrino, this is also fundamental particle. This is electron, so this is electron anti-neutrino. This is fundamental particle, this is also fundamental particle. Now we need to write down this one in terms of fundamental particles only. So in this case, 1 neutron change into proton because proton number increases by 1 and the mass number does not change. So it means total number of protons and neutrons remains same, but proton number increased by 1. It means 1 neutron change into proton. So in this case, fundamental particle we need to write down. So the fundamental particle, simply you can see the change. So in this case, 1 down quark is changing into 1 up quark. So 1 down quark is changing into 1 up quark. So simply we can say in this case, 1 down quark changes into 1 up quark because quarks are fundamental particles, and electron, this is also means beta minus particle, this is also fundamental, and antineutrino, this is also fundamental. This is electron antineutrino. So this is how you can write down beta minus decay in terms of fundamental particles. So quarks are fundamental particles, beta minus is particle is also fundamental, and antineutrino is also fundamental. For the second part, we need to use equation from B1 to show how charge is conserved in beta minus decay. Means we need to use this equation. We have down quark and the charge on down quark is minus 1 over 3 times E. And the charge on up quark is 2 by 3e, means this is plus 2 by 3e. And the charge on electron is minus 1e, means electron has negative charge. And the charge on neutrino is equal to 0. So these two are equal. We can recheck this one. So this is minus 1 over 3e. And here we have, this is 2 over 3e minus we have e. And so simply we need to check this side. So if we take LCM, so we will get 2e here minus we have 3e here. So we can simplify this one. We will get minus 1 over 3e. So as these both sides are equal, it means charge is conserved. So this is what you need to write down. So in this case, charge is conserved. Charge is conserved in this case. For part C, it is given to us neutrinos were first proposed to exist more than 20 years before they were directly detected. In order to explain a particular experimental observation about beta decay. For part C1, we need to state an observation about beta decay that is explained by the existence of neutrinos. So simply we need to explain why neutrinos were discovered before even they were detected. For that purpose, we need to understand in any beta decay, when we do experiment about beta decay, we observe that in any beta decay, always electrons, or we can simply say beta particles, they were emitted with range of kinetic energies. So if we repeat again same radioactive decay, we will observe kinetic energy of electron, or simply we can say beta particles, is different. From that we concluded that it is possible there is an other particle that is sharing kinetic energy with beta particles, and that particle was named neutrino because that particle should not have any charge. So neutrino simply means that neutral particle. So this is how neutrino were discovered, because beta particles were emitted with a range of kinetic energy. So that was the reason behind discovery of neutrinos, even they were not detected by experiments. So this is one point you need to write down in your answer. So simply you can say in this case, electrons emitted from the nucleus have a continuous range of kinetic energies. In beta particles, always they have different kinetic energy. Even the same experiment was repeated, and that was the reason behind discovery of neutrinos. For the second part, we need to suggest how the existence of neutrinos explain the observation in C1. In beta decay, we discovered that, means we found that beta particles are emitted with a range of kinetic energy in the same experiment. When we repeat the same experiment, we will see the kinetic energies of beta particles are different every time. And when neutrinos were discovered, we also observed that neutrinos also have range of kinetic energy for the same amount of energy released in any decay, or simply we can say in same experiment. If we repeat experiment, they will have range of kinetic energies. So this is how neutrinos, they explain why beta particles, they have range of kinetic energies, because beta particle and neutrinos, they share energy. So that's the reason both of them, they have range of kinetic energies. This is how you can write down your final answer. So simply you can say the emitted neutrinos take varying amounts of same total energy released in the decay, or simply you can say emitted neutrinos, they also have range of kinetic energies. So it means beta particle and neutrino, they share kinetic energies. So this is how neutrinos were discovered before any experiment. So they were discovered theoretically by observations. I hope this paper is clear to you, and we have finished this paper today, and I'll see you in next video.